started on our next topic, chapter 4, the last one for today. Last one for this week. And we're going to do an introduction to what's called probability. Probability is basically an idea that's relatively modern. It's not something that we've, in the mathematics world, have spent a lot of time on. So it's quite new. But it does have a concept that we've known for a long time. If you say things like, oh God, there's a 50-50 chance it's going to rain tomorrow, you're actually using the language of probability. If you say things like, there's no chance I'm going to get that job, you're basically using vague language of probability. Probability is a number that represents how likely something is going to happen. That's what it is, right? And a big number means it's very likely to happen, right? And a small number means that it's unlikely to happen. And probability is on a scale. And scale goes from 0 to 100%. If you do it as a decimal, which is very common, or a fraction, it's from 0 to 1. So right in the middle, you have events that have a probability of 50%, or as a decimal 0.5, or as a fraction and a half. So if I said to you, something had a probability of 50%, what I'm saying is that there's even chance that it's going to happen or not. So if I said the probability that I get a speeding ticket sometime in the next year is 50%, right? Then it doesn't mean I'm guaranteed, right? Would you agree? Half the time I will, right? Next year, half the time it happens, half the time it doesn't. Now, at the extreme ends, at 0 and 1, we have probabilities that are very, very precise. If the probability, and let's call this event A, right, whatever it is 0, that means it will not happen. So any event, anything that you're interested in putting a numerical value on how likely it is to happen, right? So any probability of event A, if it is equal to, if it's equal to 0, that means it's not going to happen. The probability that all the politicians in America are going to tell the truth today is 0. Right? The probability that I'm going to throw this pen in the air and it's going to spontaneously catch fire and then turn into an orangutan is 0, right? That's just random nonsense that came into my head, right? Certain things just aren't going to happen. Now, at the other end, you can have things where the probability is 100% or 1. And those events are guaranteed. They will happen. Whatever it is, it'll happen. So for instance, don't know, probability that, well, let's pick in politicians, that a probability that a politician's going to lie today is 1. Probability that I'm going to survive today and finish this lesson is 1, because I'm an optimist and I have no intention of killing over, right? And so on. I'm sure you can find better examples of these, right? And the further to the 100% or 1 isn't that very likely events, but not guaranteed, right? So you could have things like maybe around about here, let's say that's about 0.2. 0.2 is a chance that I get a steak dinner today. It could happen, right? But it probably won't. And away up here at 0.8 is the probability I get pizza today, which is actually very likely because I want one. Are we conceptually getting this idea of what probability is? A number that gives you an idea of how likely something is going to happen. So we've known these ideas in the past. We just didn't really put numbers on them. Liana, couldn't you say things like, my girlfriend, the chances that she's going to be with that same boy as her boyfriend next year is almost zero.
Yes.
Not right?
Yes.
Right. When you do a thing like that, you are using intuition, which is one of the 3 ways in which you can assign probabilities. Intuition is, from my past experience or from my gut feeling, I can put a percentage on a probability, right? Let's say percentages. So Liana's girlfriend, you might say, there's a 5% chance she's going to be with him next year. Right? Or, yeah, there's a 95% chance, right? You can see in both those cases, you're putting a number on an intuitive idea of what that might or might not be. Mackenzie, in your case, there's a 95% chance my dad's going to embarrass me somehow this week.
He's right over there too.
Has he successfully embarrassed you yet?
Oh no, Dad, you cannot start talking to him about our Scottish background. You gotta keep going.
Well, I think that percentage has now increased based on that conversation we've just had, right? But if you have no way of proving it, right, Liana, you can't say, well, there's a way I can, scientifically prove that my 5% that I gave her is real, right? Isn't it just an intuition, right? And if you've got good intuition, it might end up being correct. The second way that we calculate probabilities is by looking at equal chances of events happening. Well, let's look at equal chances of events happening. It works really well when the event is something that is predictable, right? Something that you can feel comfortable about. So let's have a very simple event. I'm going to roll a dice 1 time. Now, on a dice, there are 6 numbers, agreed? And would you agree that if it's a normal, nothing special about it dice, don't each one of those numbers have an equal chance of happening? That's what this is, right? Equal chance of happening. So if I say to you, what's the probability that I throw a dice, right? And I get the number 4. Well, you would say there's only 1 4 on a dice, and it's equally likely out of 6 numbers that could happen. Do you see my answer now is 1/6? I have a numerical value, which is it's about here roughly, if you wanted to see it on the scale. 1/6 is fine. It's 0.166 forever if you do it as a decimal. And it's about 16.7% if you give that same probability, but you do it as a percentage. So probability 1/6 that you get a throw, you get a 4 when you throw the dice. As a decimal, 0.166 repeater, or if you round it off, because it's probably a good idea to round it off, you get 16.7. But you can also do it for things like, what's the probability that I roll a dice and I get an even number, right? So a 2, a 4, or a 6 happens. Now, there are 3 of those, isn't there, out of 6. As a fraction, you would always expect to, reduce it as a fraction or as percentage. So when you're doing probability questions, look to see if it has a preference, because WebAssign can sometimes be kind of awkward. If it doesn't mention which one of these 3 it wants, then I'm sure you'll be fine. right? You could just put in a half, you could put in 0.5. Yeah, I'm a bit dodgy with that one, but you could put in 50%. But if it says, give the answer as a fraction, use that one. If it says, give the answer as a proportion or as a decimal, use that one. And if it says, obviously, percentage. So, I mean, if it tells you what it wants, will you do that? Because if it wants it as a percentage, but you type in a half, it's going to make you wrong. Right? If you type in a half when it wanted you to type in 50%, it's going to think you meant 0.5%. You see, it's going to say you're wrong. So just be careful. So that's the second way in which we can calculate probabilities, as long as we have a situation where it's equal. Let me try another one. So about, or hopefully you know this one, a deck of cards. Now, for some of you, you might not know playing cards that well. So here's a very, very quick description of what a deck of cards would look like. They have 4 suits: hearts, clubs, diamonds, and spades. And each one of them has 13 cards in them. And the hearts are red, and so are the diamonds. And the clubs are black, and so are the spades. And each suit, these are called suits, the 4 of them, have a whole load of cards, but basically they go ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. So hopefully you all knew that, but just for the off chance that some of you never play cards. So if I wanted to know what's the probability that I deal 1 king, I'm going to just pause for a minute here. And here we go. I'm just muting you all. I'm getting some kind of feedback that was a little bit distracting. There we go. So you want to answer the question, you'll just have to hit the space bar. Hopefully that's not a big thing. Right, back to question. If I wanted to know the probability that I get a king, there are 52 cards in a deck, and every single one of those 52, no jokers, right? Every single one of those 52 is equally like, right? And I know that there are 4 kings. So as a fraction, I get 113. Now, suppose I wanted to know the probability that I got a club. Well, there are 52 cards in a deck, and there are 13 clubs, and the answer in that case would be a quarter. Does that make sense? That it's, as long as you know all the things that could happen in a deck of cards, there are 52 cards that could happen, or in a dice there are 6 numbers that could happen. As long as you know that, you can find the probability of any event. Couldn't I even say, what's the probability that I get, I don't know, a number bigger than 7, right? Or a card less than 2, or a card between 4 and 6, right? Anything I wanted. When I just count how many there were and divide it by 52. And that is the second method where we do equal chances. And the third way of doing probabilities is using relative frequencies. And we can use these tables, relative frequency tables, to calculate the probability of an event happening. So suppose I collected ages as people, and then I got the relative frequency. But I'm going to put frequency in here as well, because that kind of helps. Right, suppose I broke people into babies. young children, and then teenagers. And so, I don't know, I went to some area, Bremerton, and I just wanted to know, you know, what's the relative distribution, right? Are there a lot of babies in Bremerton, or are they mostly teenagers, right? What kind of children do they have, right? People that have children, right? And I found in my sample, there was 10 babies, 20 young, 30, what do I call this ones? I've got to call these something. What do you call them when they're not quite teens? Do you have a name for it? Is it teenies? Pre-teens? Pre-teens will do.
Tweens.
What's that name again?
Tweens, like they're in between. Tweens.
In between, right. And there's 30 tweens, and then we finished with 20 of them, right? So in my sample, that's 30, 50, 60, 70, 80. So in my sample, there was a total of 80. Now I can turn them into relative frequencies, right? So for instance, 10 out of 80 is 1/8, so that's 0.125. That's 0.25. Oh, what's that one? I better do it in my calculator. 30 out of 80 gives me a relative frequency of 0.375, and that one ends up being 0.25. And if I did it correctly, shouldn't these add up to 1? Which they do, so I know I've done it correctly, right? So we can use a relative frequency table to calculate probabilities as well. So for instance, I could say to you, what's the probability that you pick a family and there are, or you pick a small person, that's better, and they happen to be young? Well, the answer is 20 out of 80, which would be a quarter, or you could just call it 0.25, which is its relative frequency. But you can also ask things like, what's the probability that they are not a teenager? So I'm going to do it by using these numbers here. Right, if you're not a teenager, doesn't it make you those 3 people? And those 3 people add up to, I believe, 60. And that ends up as a fraction 3/4, or 0.75. Now, if I wanted to do the same calculation, but use relative frequencies, wouldn't not being a teen be those 3 guys? And I bet you if you add those 3 guys up, won't you get 0.75? So you can calculate probabilities. So I can say that in Bremerton, if you're a child, right, you're under adult age, right? There's a 75% chance that it's not a teenager. So it gives you a kind of idea of a different way of looking at distributions, right, demographics. If you looked, changing the subject a little bit, but I'm telling you right now, because this is something that is going to happen in the future. And when it happens in the future and the politicians of the day said, well, we couldn't predict this, or how would we know this is going to happen? I'm going to tell you right now that they are lying to you, because I'm going to tell you what's about to happen. Community college professors, of which I am one, are very heavily weighted on the older age group. And I'm making a prediction that in 10 plus years, 10 to 15 years from now, there is going to be a big shortage of community college professors. And they're going to turn around and says, well, you know, what can you do? You can't just make them happen. We couldn't predict this. It's not our fault. Or the other excuse is, it's the other guy's fault, right? They should have done it, but they didn't. Well, I'm telling you right now, 10 plus years from now, there's not going to be enough university professors. I'm going to be retiring in 3 years. I know that our department is probably younger than some, They're going to be at least a 25% turnover, right? At least a quarter of the professors, if not more, are going to disappear in the next 10 years. Now, unless community colleges become smaller and have fewer students, that's going to cause a big problem to you. So I'm telling you right now, fix it. Right? The politicians are in power, fix it. Start hiring young people, even if it means hiring more than you need. Once the people retire, won't they be able to fill out the gap? There's a lot of professions right now that have that same top-heavy thing going on, right? So, telling you right off the bat, that's going to happen. Another one, just because I like moaning and mumping. If the government, because that's my favourite thing to pick on, tell you that they're going to build a new bridge, right? Let's suppose they decide that the Warren Avenue Bridge isn't worth fixing anymore, right? We're going to build a new one, right? Here's predictions. You can do it right away. It is going to cost them twice what they budget for, and it's going to take them 3 times longer to build it than they said they would. And they're going to be surprised when that happens. Do you remember the Seattle tunnel thing that they were building? Remember that one? Didn't that take longer to build than they said it would? Anybody in the military, when did they ever say, oh, we're going to build a new tank, and they got the price right and it came in on that price on schedule? Didn't it always take twice as long to get the thing to work and cost 3 times as much money? And weren't they always surprised when that happens? Since the probability of that being very high, shouldn't they not be surprised anymore? So, just got that out. All of those things I just mentioned, you could do easy predictions on it. Couldn't I do a table of the ages of Olympic College professors and say, what's the probability that that person's going to be retired in 10 years from now? Right. I don't think many of the 30-year-olds are going to be retired, right? Most of them are probably still going to be doing their job. But won't the 60s and the 70s be gone? That's what I'm talking about. So, have you gathered that I don't like politicians? Okay. So I'm going to tell you a joke about politicians then, because that's what I'm like and it's in my brain. Guy goes to the doctor and the doctor's looking really worried. So the patient's getting worried as well, says, what's up, doctor? You know, come on, tell me, what's up? So the doctor says, I've got good news for you and I've got bad news for you. So the guy says, well, better tell me the good news first then. The doctor says, you've got 6 months to live. And he kind of looks at him and said, that was the good news? He said, yeah. What's the bad news? Oh, I should have told you 6 months ago. That one didn't work. Keep going then. But the doctor says there's a chance for you. The guy says, what do you mean? He says, what you need to live is a brain transplant. And the guy says, I've never heard of a brain transplant. He says, it's a brand new cutting edge technology. It's just we're lucky we can do it. But it'll cost you. Insurance doesn't pay for it. It'll cost you. The guy says, how much? He says, look, I'll show you. And he takes him into his room and there's 3 tables. And on each table, there's a big jar of brains. And he goes to the first table and says, in this jar here, we have English professor brains. $1 an ounce. Easy to come by. $1 an ounce. We'll get you a brain. The guy's figuring out how heavy his brain is and what it would cost him. The guy says, well, that's pretty cheap. I could handle that. So he takes him to the next one. And he says, in this jar, there is math professor brains, and they're going to cost you $100 an ounce. So it's my joke. So it's math professor brains. And he goes, it's steep. I guess I could do it. And he goes to the third table and says, and in this jar, we have politician brains. and they're going to cost you $1 million an ounce. And the guy's looking at him saying, come on, $1 million, you know, $1 an ounce for English, 10, then 100 for math. How on earth could you possibly charge $1 million an ounce for a politician brain? And the doctor looked at him and said, have you any idea how many politicians you have to kill to get 1 ounce of brain? Okay, I feel so much better. In case you are picking up the wrong impression, I actually love America. I think America next to Scotland is the best place in the world. I love you. Any country that can survive what I say about them must be a pretty good country. Although, if I disappear in the next 2 weeks, I may have to change that. So, I know I've distracted the heck out of everyone. Are we comfortable about how to calculate? Intuitively, you just say what you feel, right? Then equal value, right? You throw the dice, how many 2s out of 6, that kind of thing. Card games, so on, and that's it. And then relative frequency, right? Where you collect data and you can use the table. So we can now move on to how to calculate what's called the complement of an event. Suppose I tell you that the probability that it rains tomorrow is 0.15, right, which is 15%. And you could actually do that. Couldn't you collect data from the last 100 years and find out how many times it rained, you know, on the 15th of July? And that would be a way of doing it. It would be done probably using relative frequencies. But let's just assume that we assume that that's true. Then there's a guy called the complement event. What's his name? Complement event. And it's the exact opposite of that. And we very often stick the word not in front of it. So the probability that it's not going to rain is also predictable. And the reason why this complement event is predictable, I can tell you what the probability is when I only know this one, is because either that happens or that happens. Would you agree? It's either going to rain or it's not going to rain, right? There's nothing else left. And because of that, it ends up being 0.85. Now let's see the logic of that. Since something is guaranteed to happen, doesn't that make its probability 1? Great. So if I went and said to you, the probability that it rains plus the probability that it's not going to rain, since that is the only two things that can happen, the answer has to be 1, right? And I already know that this is 0.15. So the probability of it not raining plus 0.15 is 1. And so the probability of it not raining is take that away from that. That's a bit long-winded. Obviously, you wouldn't need to write all that work. But does it make sense that if I know an event, I also know the probability of its complement? Now, we even have a fancy way of writing it. It looks like this. The probability of A plus the probability of the complement of A, they just put a little C above it. That's how you write the complement of A, is always equal to 1. Right. So if I know that it's going to, let's suppose we're in the winter, right? And if I say, oh, the chances that it snows tomorrow is 30%. Isn't the chance that it will not be snow tomorrow the other 70%? That's essentially what this is saying, right? You tell me one, I can always get the other. Might not seem that useful, but actually it can be quite useful next week when we do more complicated probabilities. This little result is actually quite helpful. Are we good? So let's do some special cases. What's the probability of something that's impossible? Well, we know the answer to that. isn't it 0? What would be the complement of this event? What's its probability of the complement of this one? They add up to 1. If this is 0, what's the complement?
1.
Yeah. Not that weird, is it? Right? It's just big. Most of the time, won't it be a number and the other one will be what's left from 1? So if one of them's a quarter, won't the complement be 3/4? If one of them's 22%, won't its complement be 78%? If one of them is 0.2, won't the other be 0.8, right? An event and its complement always add up to 1. Are we good? Right, now, kind of going through all the stuff and then we'll look at the homework. I need to find a guy I was looking for. Where are you hiding? Okay. Next thing we're going to look at is called the law of large numbers. Which is what this textbook calls it, number 4. I much prefer this phrase. Now, apart from being a mouthful, isn't that phrase very pretentious? The empirical phenomena of statistical regularity. It's the same thing as the law of large numbers. If you are in the medical field, I would say I broke my arm. And a doctor would come up with, you have had a fracture in your tibia or whatever. I think your tibia is in your leg, actually. But wouldn't they come up with some Latin word for what that bone was called? And if you're a human being, don't you just want to know you broke your arm? You don't want to know that you fractured your tibia muscula or whatever the damn things are called, right? Zach, you are laughing. Has that happened in your life that the doctors say things in that format when they could just say your big toe hurts?
No, I'm a kinesiology major, so I was just laughing at your terminology.
Oh, I screwed it up totally, didn't I?
Yeah.
Yeah. But the
Okay.
idea behind it. Now, I guess there's a reason for it. It's for preciseness, isn't it? You know, so if you say it in that way, people know exactly which part of the arm's broken or which part of your big toe is not working right or whatever it might be. And if you know the Latin version of it, I think, is medicine mostly Latin or is there some Greek thrown in there for fun?
It's pretty much all Latin.
It's all Latin.
Right. So if you know enough Latin, even if you've never heard of it, couldn't you tell by the name of it where in the body it was happening and what's probably gone wrong? Right. So fracture, I think that's what they would call it when that means something broken in my terminology, right? And what would a contusion mean?
Bruise.
Bruce. Rupture.
I mean, rupture is self-explanatory. It broke like it.
Okay. So you see, the people in the medical world need that language, but don't you only need it to talk to each other? But when you want to talk to your patient, you probably wouldn't want to use those terms. Agreed? Wouldn't you say you've bruised your elbow or you've broken your big toe, right? So this is the equivalent. The law of large numbers is what you should really talk about. The empirical phenomena of statistical regularity is the same thing. So let's tell you what it means. let's suppose I want to know the probability that in a street there's going to be a car accident tomorrow, right? So we've got a big long street and I want to know if there's a car accident on any given day, right? So what's the probability at least one car accident, right? Big enough or important enough for the police to turn up, right? So we're not talking about little, you bumped into my fender, but be careful next time. Nothing like that, right? Something that's noticeable. Well, what you could do is you would collect data to try and predict this probability, right? You can't do it theoretically, right? Every street's different, isn't there? Some streets quite dangerous and other streets, you never get an accident virtually. So imagine you collected some data and it will look like N is the number of days, right? And here we had whether or not there was an accident, right? So you got 100 days and there was 5 accidents, right? So whenever it was to wherever it was, you collected data and there was 5 accidents in that 100-day period. And so that would come out as roughly 0.05. That's our relative frequency guy. And that's good. As a prediction, wouldn't you say that the chances there's going to be an accident on this street on any given day is probably about 5% chance? And you could use that to compare this street to some other street. Make it up. Suppose there was a street where the chances that there were going to be an accident is 15% on any given day. Wouldn't you call that street a very dangerous street? And wouldn't you want to do something about reducing accidents? And there are lots of ways to reduce accidents. Couldn't you put those little things that tell you your speed to make you slow down? Couldn't you just get a police car to be there all the time visible? That'll slow people down, right? Because speed is one of the ways you cause that. Couldn't you do something about improving the road? Maybe it's the roads are too narrow, they're too bend, whatever it is, right? Whatever it is, 5%. Now, you collect data over 1,000. And when you collected it over 1,000, you found out there were 51 accidents that happened. And that ends up being 0.051. Do you notice that my next prediction is a little bit different from the first one? Does that seem reasonable? You wouldn't expect the exact rate. Isn't this just what happens, right? And let's suppose you got data on 10,000 days. That's like 30 years history. And when you did this one, it's 507. Which ends up being 0.0507. Would it seem reasonable that your most accurate prediction should be based on the greatest amount of times that you measured it? And that's what the law of large numbers says. It says that if you are estimating or trying to calculate a probability, the more numbers that you've got in your data set is going to give you a more accurate answer. Now you can do that, and they did do it, so at least they did it through computers, by the usual throw a coin in the air and see what happens. What fraction of the time you get a tail. And this is what they discovered, and it's kind of cool. And basically what they got is they got a computer to simulate throwing a coin, right? So if a 1 appeared, it was a tail. If a 0 appeared, it meant it was a head, right? And they just got the computer to randomly generate millions of zeros or ones, right, in randomness. And right in the middle, little dotted line, isn't that what the probability of getting a tail should be? Shouldn't it be a half? Right, if you throw a coin in there, what's the probability that you get a tail? It should be about half. Right, so you did 0 times, you did 10, you did 20, you did 30, 40, 50. Actually, they did it with like 30 million and 40 million because computers can do it forever. And this is what they got. The answer was there, and then it 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 was there. And if you join it up, do you see that what is happening is that although you're not getting 0.5 all the time, aren't you getting less and less variation? Isn't it homing in on 0.5? And that's what the law of large numbers also tells us, right? That the more times you do an experiment, the relative frequency of successes over the total should home in on the probability. So how can we use that? Well, you can use it to predict probabilities, right? Relative frequencies can be used to predict probabilities. This is just a visualization of the same thing. But it doesn't mean the following. Let's suppose I physically threw 100 coins in the air, and I've got to 99 I've already done. And when I did the 99, just by fluke or whatever it is, I have 49 heads happened and 50 tails has happened, just for the sake of my story, right? Just imagine that's what happened, right? I'm about to throw my last throw. What's the probability that it's going to be a head? So here's your choices. Is it more than a half? Is it less than a half? Or it's still 1/2. Which of those is the probability of my 100th throw of my coin that it's going to be a head? Where are you going? Oh, come on, you have a 1 in 3 chance probability of guessing correctly. Where are you going for, Zach?
I think it's going to be heads.
So is the chance that this last one's a head, is it going to be more than a half? Is
Yeah.
it still more than a half? Right. Okay. I'm glad you answered, because I got an answer. And I'm not going to tell you it's not correct. And you have fallen into what's called the Monte Carlo fallacy, which most people fall into. It's still a half. And you're thinking, but wait a minute, you said the probability is a half, so shouldn't that be a head so that it's 50-50 and you get the half, right? Which is kind of what your logic would be, right? That's what you're thinking. It's not. Every time you throw a coin, the probability of it being a head is a half. Every single one of those 100 throws. And even if 99 have happened and you've got this split, it doesn't mean. Let's try and maybe explain why that must be the case. For your answer to be true, Zach, wouldn't that coin need to have some kind of conscious thought? It would need to know that it had 50 tails and 49 heads the last 100 times it had been thrown. Right? It's an inanimate object. That seems highly implausible. Secondly, wouldn't the coin have to have the wish to balance things? Oh, I'm one short of being 50-50 here. When that guy throws me in the air, I'm going to give a quick twitch and move it so it lands on the head. You see how that doesn't work? Anytime you look at a probability of an event, it is totally independent of what happens in the past. So although the laws of large numbers says that things level off, which it does, it tells you nothing about one coin being thrown at any point in the process. That single one coin. Now, the reason it's called Monte Carlo fallacy, well, the Monte Carlo part's easy. There's a casino called Monte Carlo, right? There were two different gambling strategies, both of which were wrong. But the people in Monte Carlo loved it because it encouraged more gambling. So instead of heads and coins, let's say it was a roulette table and it was a red number and a black number, right? They also have a green number, but that's just to help them win more money, right? Red number and green number. And there's been lots of times in Monte Carlo when there was 10 run numbers in a row. And what would typically happen, that once something like that happened, people started getting interested in the roulette table, and more people would come over and they'd say, oh, 10 reds in a row. And they had two strategies. One bunch of them said, reds are hot tonight, and they would bet a load of money on the next roll being red. And another bunch of people also looked at that, but they saw it a different way. Hey, these things are meant to be balanced, right? 50-50 chance of a red, 50-50 chance in a black. Isn't it time now for the board to turn? And they put a wad of money on the black. But in reality, when you put that ball and you spin it round in the roulette table, like in the James Bond movies, isn't the red and the black got an equal chance of turning up, red or black? And it didn't matter that it had 10 reds previously. As long as there's no cheating going on, it doesn't matter, right?
On roulette, would it still be 50-50 because you got that one white in there?
Yeah, that alters the rule a little bit. Yeah, in fact, they're green, at least the ones I've seen. But yeah, but the gist of what I'm saying still stands,
Okay.
right? It's called the Monte Carlo fallacy. But Monte Carlo loved it because there've been a lot of people lost a lot of money using that bad idea. So I think I've covered everything. So I now want to show you what the homework looks like. Oh no, I did miss one thing. This guy. I am going to write down some probabilities. We'll call them A. And what they were equal to. And all we need to do is decide, are these probabilities even possible, right? So this one is a half. This one is 0.8. This one is negative 0.2. This one is 7/4. And this one is 3/100. So let's start at the top. Could you get a probability equal to a half? Check. Agreed. Could you get a probability of 0.8? Agreed. Could you get a probability of negative 0.2? No. Aren't all probabilities between 0 and 1 or 0 and 100%, right? You can't get more than 100%, you can't get less than 0. Could you get a probability of 7/4 then? That is bigger than 1. Could you get a probability of 3/101? Yes. Pretty easy question to answer, isn't it? If the number is between 0 and 1, right, as a fraction or a decimal, it's possible. If it's outside that range, it's not theoretically possible. Right? Analogy. Does it ever annoy you when a manager says, we're going to give 110% effort? Because it annoys me. Can you only give everything, which is 100% effort? Now, I know what the phrase means, right? But it's just an exaggeration. And I don't like inconsistencies. That phrase bugs me. Right, let's show you the homework now. Oh, someone in the chat, should I be aware of? Yeah, you're correct, Aidan. You did say it was still a half, and you were right about the Monte Carlo story, I'm assuming. Right. So, way back at the start of today, I mentioned 3 different ways of getting probabilities. Can anyone remember them?
Intuition, Equally likely outcomes, relative frequency.
Agreed. Pretty easy to do. Homework. This homework's not actually that big. Now, suppose a newspaper states that the probability of rain today is 40%. What is the complementary of the event rain today? So what sentence is that? What is the opposite of rain today?
No rain today.
No rain today.
Yeah. Isn't this much more like an English class? How do you say the negative of a statement? And what the probability of that? Oh, and there you go. Enter your answer to 2 decimal places. So that would mean 0.60, wouldn't it, in this question? If I had put in 60%, there's a very, very good chance that WebAssign would say I was wrong. And it's not that the answer was wrong, it's the form that I wrote the answer that was wrong. So that's what I'm getting at about, you know, don't write 3/5, right? Don't write 60%, right? Write 0.6. If that's what they were asking for, you know, do it that way. Haven't we covered these two? But I guess for completeness, what's the probability that an event A, when it's certain to occur? What's the probability of something that's certain to happen? What number?
100% if it's certain.
Yeah. I'm putting in 1 and impossible is 0. The reason I'm not going to put percentages in is that, see, outside the box, there'll be a little percentage symbol. And then I would know to put 100 and 0. I mean, it's little tricks like that. And there's the law of large numbers, so I'll let you worry about that one. Now, it's talking about, what was it talking about anyway? Yeah, it's just talking about doing things 300 times or 500 times. It doesn't have the Monte Carlo fallacy question 4. Now, in a recent survey of 1,030 adults, 689 considered firefighters to have very great prestige. Yeah, I would be one of those. Estimate the probability to the nearest 100th. So that basically means a decimal. And won't we get the 689 out of 1,030? That would be using relative frequency, isn't it? That's what we're doing. And they want it to be a decimal, so that won't be the way I'll write the answer. I'll calculate that.
66.89.
Thank you. Is that as a percentage?
Yeah.
Right, now, do they mention percentages? Not to the 100. Ah, darn it. Right, 66.89% or 0.67 as a decimal, right? That's the same thing, rounded off. Which do you think they're asking for?
Decimal.
Yeah. So I'm not saying that that's wrong, because in fact it's right, but isn't it not the form they're looking for? If they want percentages, look for a little percentage. So you actually never need to type in percentage, right? You should never need to do that. Now, suppose you're looking at 4 children in the family. Assume that the probability of one child as a boy is 0.5, so that means getting a girl is the other 0.5, and that they're independent, which we can assume. List all the equal likely events. And I'm going to tell you right now, there's a lot of them. And that question is silly, because every single one of them is true. What it does help you is if you count through these, do you know that there are 16 things that could happen? So if you had 4 children in your family, there are 16 different ways that family could have been generated, right? You may have 3 boys and then finish with a girl, right? You may go boy, girl, right? That kind of thing. That 16 of all those check marks are there. So when it says, what's the probability that all 4 children are males? there's only one of those out of 16. And that's the answer as a fraction. And they tell you, fraction. Now, it says, notice that the complement of the event, all 4 children are male, is at least one of the children is a female. Now, if you're into English and logic, does that make sense? The opposite of all 4 being males, right? The opposite of that is at least one of them has to be a female. Okay. If it's not all 4 boys, what does that mean you've got? Well, doesn't that mean you've got all 4 are girls? Or 3 of them are girls and one's a boy? Or 2 of them are a girl and 2 are a boy? Or 3 of them are a girl, 1 are a boy, right? In other words, at least one of them's a girl. So that's what it means. Now, it asks you to use this information to calculate the probability at least one of the children is females. Well, that is a very long-winded way of getting you to do the complement. Right? If they're only one way out of 16 you're getting 4 boys, isn't there 15 out of 16? Did I put the 16 in? 15 out of 16 ways of not getting 4 boys. Got puzzled in that, Saka? You okay? You're good, okay. That's question 7 is a miniature version of the Monte Carlo story that we did. Question 8 is, are these possible? So let's do a couple of those ones. Out of the 4 guys, A, B, C, or D, which one of those 4 is actually the only one that's possible for a probability? Only one of those 4 answers is actually possible as a probability of an event. Which one is it?
Would it be D?
Yeah. Remember, you can only be between 0 and 1 or 0 and 100%. Okay, so let's look at the first one. Would you agree that's not possible, right? Why is it not possible, right? So you have to give a kind of justification. A probability must be between 0 and 1, right? That's that one. Right, let's make this a little bit bigger because I'm not sure what kind of screens you might have. Right. Would you agree that 1.21 is too big? Isn't it bigger than 1? So it's no. And that answer again. And this one's okay, isn't it? So it's yes. And that answer again. Okay, this is a weird question. Can you wiggle your ears? No, I cannot. Can anybody here wiggle their ears? You can't, Aidan. You know, that might be a useful skill one day, but I can't think of why it might be. Evidently, it's quite rare. Use the students in your class or group of friends to estimate the percentage of people who can wiggle their ears. Okay, so in our class, there are, including me, 3, 6, 9, 10. Great number. I like 10, easy to divide by. Aidan can wiggle his ears. Anybody else? Not without hands. Rosie, can you wiggle your ears without doing it? Okay. So it looks like for us, wouldn't the answer be 2 out of 10? Right? 2 people out of the entire class of 10 of us. Okay. We have just done what they asked us. Now it goes on and says, so our answer was 2 out of 10, right? 0.2. How can your results be thought of as an estimate for the probability that a person choosing at random can wiggle his or her ears? And a little piece of information. Do you know that the national statistics indicate that about 13% of Americans can do it? So, what's that? About 1 in 7 Americans can do it. So our class was 20%. That's a little bit of an overestimate. But would you agree our sample is tiny, right? We only had 10 people to pick from. I bet you if you did the same thing with everybody at Olympic College, wouldn't we probably get an answer much closer to 13%? Right? And then it says, the resultant relative, well, one of these sentences at least, the resultant relative frequency can be used as an estimate for the true probability of Americans who cannot wiggle their ears. Cannot? That's the wrong one. The resulting relative is the true probability, definitely not the true probability. The resulting relative can be used as an estimate for the true probability. There we go, it's that one there. Now, here we have I don't know how realistic it is. Social scientists people spend a lot of time doing stupid things, and this is one of them in my opinion. Isabel Briggs Myers was a pioneer of the study of personality types. You know, this is a great way of making lots of money, in my opinion. Publish a book, become famous about personality types, get it connected to business or education. That's the two places to get the money, right? The big bucks. And can you imagine her going to different big companies and saying, these are the kind of personality types that are successful in business, you know, and doing all that kind of nonsense, right? Motivational speakers. You know how much money motivational speakers get? Yeah.
They actually had a personality test that a lot of businesses were using, and they got sued for it because they were saying that they were empaths or certain types of not empaths, and they were discriminating on hiring people for it. They took to court over it.
I'm not surprised. You know, it's pseudoscience at
Yeah.
best. I don't think. If you know what they're expecting, won't you do the test and answer it the way they want the answers to be? In other words, you lie. And if you're truthful, it's a waste of time. Anyway, back to this one. If you want to know married couples, somebody analysed how many things that they had that were similar to each other, right? Like, we had the same sense of humour, right? We had the same opinion on finances, right? We had the same politics, whatever it was. And they picked 4, I guess the 4 major ones, and they found out that married couples who shared all 4, out of the 375 that they tested, only 27 of them had all 4. If you had 3 out of the 4, that's 130. If 2 out of the 4, you would have this, 1 out of the 4, and there's the last one. So, I mean, just looking at that raw data, the chances that you and your partner are still married, wouldn't it be a good idea not to share everything in common, but to have some differences? I don't know if that is even vaguely true. I think I'm actually glad my wife's not here. She might disagree, but I'm actually happily married. And me and my wife have more things in common in some respects, and we are totally different in others. My wife loves jazz and rap music. I absolutely detest jazz and rap music, right? Can you imagine the issues in driving long journeys in a car? We have a rule: the person who's driving plays the music, which seems fair, except we have a second rule, which is when we drive long distances, my wife drives. So I think that first rule isn't fair when you incorporate the second rule. Agreed? But evidently my wife thinks that's fair. But then there are lots of things that we do share. We love travel. Me and my wife love traveling foreign countries. We've been in lots of places, enjoyed it. We love foreign food, which is part of travel, right? We share that. So I don't think none or any of those really mattered as far as us being able to stay married for the length of time that we did. I think they're very. If you end up divorcing somebody because you don't like the music they played, you probably weren't in a very serious relationship to start with. So I don't think it's the music that did it. Anyway, I'm writing on. Back to this one. That guy there is 27 out of 375. Whoops. Right, that's the relative frequency. Now, they want the answer to 2 decimal places. Isn't that the clue that they want me to do 27 divided by 375 and come up with the answer, well, 0.07 is what it rounds off to. So 7% of successful marriages, both partners shared all the same major, things, whatever those 4 ended up being. And I forgot to put a 0.7 in there. There we go. Can you imagine doing all of them all the way down to the end? All right. Do these probabilities add up to 1? Well, can you imagine I did them all? Theoretically, shouldn't they all add up to 1? But in practice, couldn't you get 0.99 or 0.98? Or couldn't you even get 1.01? Why could that happen and still not be a mistake? Well, I rounded off, didn't I? And couldn't sometimes I round up more often than I rounded down? So couldn't the net effect be the answer's a little bit bigger than 1? Or a little bit less than 1? So yes, but they don't always work out that way. Now it says, here's a word. What is the sample space? The sample space means what is a list of all the things that could happen. So in this case, the sample space is 0, 1, 2, 3, 4. Agreed? 0, 1, 2, 3, 4. Moving on. If you roll a single dice, so we did this one early on today, didn't we? Aren't there 6 things that could happen when you roll a dice? Right? You could get a 1, you could get a 2, you could get a 3. So equally likely events, yes. So won't that be my sample space? That's the 6 things that could happen. Oh, I got 0 in there. There we go. There's the right answer. Isn't the 6 things that could happen 1, 2, 3, 4, 5, 6, and aren't they all equally likely? So what's the probability that I roll a dice and I get a 1? The answer is, as a fraction, 1/6. Actually, isn't the answer 1/6 for all of them? So it's a pretty boring table, really. Do these probabilities add up to 1? Sure do. In fact, as long as I haven't rounded off, isn't it guaranteed? What's the probability of getting a number less than 3? If you say less than 3, does that mean 3 gets counted or not? No, right? Less than 3 means what? It means only these 2 events, right? That one and that one. And so wouldn't the chances be 2 out of 6 then? Which you would simplify down to 1/3. And there's another question you could answer in the same way. Here's one. When do creative people get their best ideas? Right, like when does a musician get that like combination of notes that, off he goes and, does his thing? Or when does a businessman come up with his clever, publicity idea or whatever it may, movie idea? Well, they looked at inventors, so I'm assuming these are people who, make patents for USBs and all that kind of stuff. And they said, when did you get your ideas? And 274 of them got them from 6 o'clock in the morning to noon. And 242 of them came up with their ideas from midnight to 6 a.m. Now, when you look at those 4 numbers, and I think they're equally spaced, aren't they? Yeah, they're all 6-hour intervals. Do you notice that they're not equal? Right. In fact, looking at this data, didn't they get their bright ideas the most often in that 3rd time period, which is 6 p.m. to midnight? Now, if I'm in charge of a research and development for a big company, and I've got scientists working for me, and they're thinking about when they should, the next big idea or what's going on, aren't I wasting my time and their time by having them work 9 till 5? Wouldn't it be better just saying, yeah, go and have some fun during the day, and then at night time when you get your bright ideas, send them to me? Because in this case, wouldn't that be the most likely time that they're going to get their clever ideas? Now, that doesn't work for everybody. I'll tell you me. I am a morning person. I'm not saying I'm great, but I'm better in the morning than any other time of the day. That's me. Some people, or I guess daytime, right? As long as it's 12 o'clock, I'm finally awake, right? That's when I do my best stuff, right? That's when I learn best. I guess I'm an evening person. I'm not. God, I teach classes in the evening. I pity the students who get me. Rosie, have you ever had me for an evening class?
I have not. I've always had you for a morning class.
Good girl. If you ever have me for an evening class, you probably won't want me the next time. I make mistakes, but towards the end of the day, I'm just thinking now, I need to go and watch TV, and I'm hungry and all sorts of other things. And God, no, I'd be a zombie if you ever asked me to teach in that time interval. Just out of curiosity. Zach, when is your best time? When do you like working or thinking, or when's your brain sharpest?
Usually in the morning, like you, 6 a.m. to 12.
Rosie, where's your window of I'm best at this time?
Afternoon.
Afternoon. What about you, Aidan?
I'm also afternoon.
Right.
Noon to 6.
Yeah. So can you see, I don't know if we've got any person here who, my dad, my dad was a coal miner all his working life, but my dad hated shifts. He working down a coal mine, he wanted to work only during the normal 9 to 5 window, right? And he hated night shift because night shift in a coal mine was the most dangerous time to work in a coal mine, because there are too many tired people, and tired people make mistakes, and mistakes in coal mines don't go well together. And Zach, are you saying the same in military or whatever your experience was?
Yeah, absolutely. Whenever you're sleep deprived, it's always recipe for danger in
Right,
any job, any dangerous job.
Yeah, so don't become not don't become a nurse, but make sure you're really rested.
Rested,
Because
yeah.
nurses do some really weird hours, don't you guys? Yeah, if you admit it, because people don't get sick from 9 to 5, right? That's not the way things work.
Correct.
And so you gotta be aware of that. And so I'm pretty sure that's something that nursing tell you, right? I don't care what shift you've got, you make sure you've rested before you come to work.
Yeah, most of our night shifters will come in with like 2 coffees, 2 energy drinks, and let it ride for the next 12 hours.
Oh God, no, that doesn't sound healthy. Couldn't they just
Yeah.
go to bed for 8 hours like a normal human being and not have drugs in them?
Well, you're sleeping in the middle of the day and the sun's still out. So like, and everybody's normally like up
Making
and
a
doing
racket.
things
Gotcha.
a normal time frame. So you have to have like blackout curtains. Hopefully the kids in the neighborhood are quiet, which is not a thing.
Gotcha. I hear, right. The reality of life gets in the way of the theory. Yeah, I shouldn't really have pushed that too much. Right, here is one about germinating seeds. And so this person got 3,000 seeds and he planted them, and he only got 2,060 germinated. I guess farmers know that you plant a whole load of stuff and not all of them, come out the ground. So you tend to overplant, don't you, and then weed them out a little bit later once, seedlings appear. And so you've been asked to use the relative frequency. In this case, won't it be 2060 out of 3000, which goes there? And what's the chance that it doesn't germinate? I know this isn't the answer, but let's pretend it was. Suppose that one was 0.75. Don't I know the answer to this one is 0.249 without doing any real calculations? If that's the 3 decimal probability that my seed will germinate, how do I know that that is the 3 decimal answer for it not germinating? I've used a property to do that. Complementary event adds up to 1, that row. And a couple of questions like that. I think we're about done here. Right, so let's see what the last question is. John runs a computer software store. Yesterday, John counted 123 people who walked by the store. So I better write that down because there are a lot of numbers going on here. 123 people, they're the ones who walked by the store. "58 of those people, I guess, didn't really walk by. 58 of them came in. Okay, which must mean that if you take 123 and subtract 58 from it, the other 65 walked on by, right? And I'll read on a little bit more. Of the 58 who came into the store, 25 bought something, which must mean that if you take 58 and take away 25 from it, that must mean that the other 33, you got nothing from them, right? They had a look around and then they left. Okay, now I'm going to show you how I wrote that information down. I did it like that. I like visuals, right? So there was 123 people who, looked in the window, whatever, were near the store. There's the 58 that came in, and there's the 65 that walked on by. Would you agree the people who walked on by never bought anything, right? Because they walked on by. Now, the 58 who get into the store, 25 did buy something, and the other 33 didn't, right? They bought nothing. So we've been asked then from this chart to calculate some probabilities, estimate, right? Because it's based on just one day's results. The probability that a person who walks by the store will enter it. So 123 people walked by and 58 would enter it. Would you agree that's the answer? And they want it to 2 decimal places. So I'll now convert it by dividing. And the answer I get, rounded off to 2 decimal places, is about that. So I guess you could say 47% of the people who, see my store, slightly less than half actually come in. Now, question B says, estimate that the probability that a person who walked by our store will buy something. Well, there are 123 people who walked by my store. At the end of the day, wasn't it only 25 people who ended up buying something? Right? 123, 25 people. In this case, 25 divided by 123, and comes out to be 0.20. So if I was interested in collecting some data about this store, this number here is quite low. Only 20% of the people who could come in, right, or at least seen my store, right? Only 20% of the people buy something. If you want to be successful, wouldn't you probably want to make that number bigger? How do you do that? Well, they do the classic ones, don't they? Say sale today, 40% off, red tag items, Hey, we've got this new gizmo that nobody else has got. Come into our store. You know, whatever it is, advertise, you know, get them in. You want that to be big. Because if that's big, won't you sell stuff? And selling stuff means you make money. Now, C says, estimate the probability that a person who walked by the store, I've just done that one. Oh, that guy, I apologize, is C. Question B is, somebody who walked into the store, which is 58. What did that do? Well, that comes out to be 25 divided by 58, and that's 43%. Well, that's much better. I mean, if you put this number, which is people who come into your store, about 43% of them buy it, as opposed to this number, right, which is people who walked by, only 20%. Can you see that if you get more people to come in, won't you make more money? I mean, when you look at it like that, right? If you can get more than 20% to come into your store, 43%, if you get them in the front door, 43% of them end up buying something before they go, right? Now it says, estimate the probability that a person who comes into the store will buy nothing. Now, since this is a person that comes into the store, we're talking about only those 58, and the ones who buy nothing are 33. And so 33 divided by 58 is 0.57. And I just realized, couldn't have done that question much quicker by just doing the complement of that event. And that would have also been 0.57. And what have we learnt today? We've learnt I don't like politicians, that some of you can wiggle your ears, and that you have to be careful when you're gambling because of the Monte Carlo thing, that probabilities can only be between 0 and 1, and that there are 3 major ways in which you can calculate probabilities: intuition, relative frequency, which essentially is this, or equal likely events.